As you might expect, we're now going to look at the second case of the Cauchy-Euler equation. So what happens if the auxiliary equation of our Cauchy-Euler equation has one real repeated root, right? And you'll see a close similarity with how we're going to handle this case as to how we handled the case where we had constant coefficients. And let's start with a concrete example, though. I mean, we could go through and do it symbolically. It gets a little bit messier, but let's take a look at this differential equation. So our x squared y double prime minus 7x y prime and then plus 16 y is equal to 0. Right? And we can see that this fits our Cauchy-Euler pattern. Again, you can see that each derivative, right, is multiplied by a power of x, and that power is equivalent to the order of the derivative. You have an x squared multiplying a y double prime, x to the first power multiplying your y prime, and technically there's an x to the 0th power here, and you're multiplying the 0th derivative of y, which means you haven't taken a derivative yet. So let's write down the auxiliary equation. Now remember the pattern here. This first term, so your leading coefficient is 1, constant coefficient that is, and then you have your x squared, and then you have m times the quantity m minus 1, and then minus 7 times m plus 16, and then that has to be equal to 0. So now let's write this quadratic in its standard form, and let's see what we have. We have m squared minus m minus 7m plus 16 is equal to 0. We have a pair of like terms in the middle, so we have m squared minus 8m plus 16. That's equal to 0. And then if you look closely, you can see that this is in fact a perfect square. So you have your m, the quantity m minus 4 squared, that's equal to 0. So therefore, our m1 and m2 is the same, right? So what does this mean? Well, it means we have one of the two functions that we need to form our fundamental set, and that function is y1 equals x to the 4th power. All right, so what do we do? What do we do to get our y2? Well, we're going to follow that same reduction of order process, right? That was discovered by D'Alembert. So by the reduction of order, what do we seek? Well, we seek y2 of the form, and since we can't just, we can't just duplicate this and say x to the, like c1 times x to the 4th plus c2 times x to the 4th. No, we can't take a constant times this, or two different constants times this. We're not going to get our fundamental set. So instead of multiplying, thinking of this as being multiplied by a constant, we're going to use this process of saying, okay, can we find a u of x, so a function times x to the 4th, such that, again, we want this second function also to be a solution of the differential equation, right? So what we're going to do is assume that this, our second function of this form will satisfy the differential equation, and then see what has to be true about the function u of x, right? So let's think about it. So in this case, again, we can still think of this as a linear differential operator, right? So now we're going to say, well, what happens well, we know what we want it to happen. We want that this function, when it passes through this differential operator, to give an answer of 0, right? So we need the first and second derivatives. So let's differentiate y2 once. Now, because again, we're multiplying by a function of x, we just don't know what the function is. That's our goal, is to figure out what u is. We have to use our product rule, right? So I'm going to say u prime of x times x to the fourth, and then plus, and then u of x times 4x cubed. And I mean, not much we can do to simplify this, but what I will do is I will go ahead and put the 4. Actually, you know what? Let's just leave it in that form. I mean, we could put the constant in front, but it's fine. We can leave it in that form. So let's get the second derivative now. So y2 double prime. So, you know, if you love the product rule, the good news is we get to use the product rule twice, right? So applying it to this product, it's now going to be u double prime of x times x to the fourth plus u prime of x times 4x cubed, plus, now moving to the second term here, again we need to do our product rule. So we'll have u prime of x times 4x cubed plus u of x times 12x squared. All right. Now, with the second derivative, we can do a little bit of simplification, because here we have, you know, again, think of the 4 being in front here, and it's the exact same expression here. So you basically have 4 times u prime x cubed plus another 4 u prime times x cubed. So our second derivative can be simplified just slightly to look like this. The 4x, basically it's 4x cubed plus 4x cubed times u prime. So you'll have 8x cubed u prime of x plus 12x squared u of x. I have my parentheses too early. There we go, u of x, all right? So then what do we do with the, you know, the first and second derivatives? Well, we're going to plug it into the differential equation, right? So we're going to do what the differential equation says, set it equal to 0, and see what happens. So let me scroll down a little bit. So our differential equation says take x squared and multiply the second derivative. So I'm going to put my second derivative in parentheses. And then after that, we'll go ahead and distribute the x squared. So we have that. And then we have that. So, and then we have minus 7x times the first derivative, which is u prime of x times x to the fourth plus u of x times 4x cubed, and then plus 16 times our original function. And again, we want the second function to be of this form. So it's 16 times u of x times x to the fourth. And again, if this is going to satisfy the differential equation, then again, this is what our differential operator will produce. But since it's now a homogeneous equation, then we would want all of this to be the 0 functions. It would have to be identically equal to 0. All right. Now, surely, you know, something should happen that would allow us to simplify. Well, the only way we're going to see that is to do our algebra. So let's distribute the x squared. So we'll have u prime of x times x to the sixth plus 8x to the fifth u prime of x plus 12x to the fourth u of x. Now distribute the negative 7x, so we'll have minus 7x u prime of x. Well, actually, this will be x to the fifth. Let's just combine the x's right now. And then minus, what's that, 28 x to the fourth u of x. And then our final term here is plus 16 u of x times x to the fourth. And again, we want that to be equal to 0. So let's first look at the terms that have, like, let's start with the smallest power of x that we see here. Well, we have x to the fourth. Well, we have a 12x to the fourth plus a 16x to the fourth. That's 28x to the fourth. And then there's a minus 28x to the fourth. And they're all being multiplied by u of x. So these terms go away. It's like we just know that some stuff's going to go away. There's no way it's going to remain this complicated. What else happens? Well, if we look at the, not much. I mean, we have a pair of terms, but the x to the fifth power, and we have a positive 8 here, and then a minus 7 there. And then we only have one term that has an x to the sixth. So we're going to have this. We have u prime of x times x to the sixth, and then we have plus u prime of x, right? So u double prime of x times x to the sixth plus u prime of x times x to the fifth, and then that has to be equal to 0. Okay, things are looking good. We could factor out an x to the fifth, right? And then that leaves us with the u double prime of x times x plus u prime of x is equal to 0. Now remember, based on what we established using the uniqueness, the existence and uniqueness theorem for the Cauchy-Euler equations, we are solving our Cauchy-Euler equations under the assumption that x is greater than 0. So we're using that as our interval of existence. So since x is positive, then this factor can't be 0. So the only way this product can be equal to 0 is if the remaining factor, right, has to be equal to 0. So this implies u prime of x u double prime of x times x plus u prime of x must be equal to 0. Now, that's a lot more manageable than what we had just a few lines above. The problem is, this is still a second order differential equation. It's linear. It's good that it's linear, but you know, it's not readily apparent what u would have to be in order to satisfy this. So here's another trick that we can add to our collection of tricks as far as differential equations are concerned. I'm going to make a substitution, right? But it's not going to be of the type that we saw previously. So I'm going to say this: let v of x be u prime of x. So that means v prime of x is u double prime of x. Why am I doing this? Well, with this substitution, I can actually convert this second order linear equation into a first order linear equation. Because look at what I'll be able to do. I will be able to replace this with a new, essentially, function that doesn't have a derivative in there. So this is going to be my v. And then I can replace u double prime with v prime, and then of course I'm not changing the independent variable, so I'll still have an x there. So the equation looks like, so this gives me v prime of x times x plus v is equal to 0, right? So let's if we were to write this, let's say I switch from the prime notation to the Leibniz notation. This is saying dv dx times x plus v is equal to 0. And in fact, this differential equation is both linear and separable. So I'm going to use separation of variables, try to figure out what v has to be, right? Or at least figure out one solution here, because that's all we need. We just need one function that would satisfy this. And once I figure out v, maybe I can go back here and figure out u. Maybe. Let's see if that will work. Okay, so to separate this, I'm going to subtract the, okay, so yeah, it looks like this. So you'll have dv dx times x is equal to negative v. And so let's do this. Multiply by dx and then divide both sides by x and by v. So I end up with this. 1 over v dv is equal to negative 1 over x dx. Integrating both sides, and again we get to use this condition here. So variables are positive. So when we integrate both sides, we're going to end up with the natural log of v is equal to negative the natural log of x plus c. Okay, so we don't want it in the implicit form. So let's try to isolate the v. And I'll show you another way that you can, let's do a slightly different set of algebraic steps. If I add the natural log of x to both sides, so I'll have this plus the natural log of x is equal to c. Then I can use the properties of logs and combine these two logs as the log of vx is equal to c. Then use my exponential function, and it's a nice way to get rid of the ln. So then v times x is e to the c, and I'm just going to call e to the c my new constant k. Now, because I want, so then let's say this. So that means my v is the function k over x, right? I am going to take k equals 1 because I only need one function to satisfy this. I just need to figure out one u that will make my y2 be a solution and be linearly independent. So I'm going to take k to be equal to 1. So this implies that v is 1 over x. So if v is 1 over x, look at what happens here. If I put 1 over x here, I can then figure out what u prime, or what u is, right? So I'm going to go back down. So therefore, 1 over x is equal to u prime. So what function do I know when I differentiate it gives me 1 over x? Well, it turns out then that's our same natural log. So u of x would have to be the natural log of x, right? So this function now will work. It will guarantee that my y2 is in fact a solution of the differential equation, right? And then let's to establish linear independence, we can use our Wronskian. So let's kind of summarize where we are now. So hence, we now have two functions, or y2 is y1 is x to the 4th, right? That one we got just by doing basic algebra. This one, we had to do a lot more work to get it, but y2 is going to be the natural log of x times x to the 4th, right? So then we have to, so let's see, our two solutions, right, of the dE. Can I call them a fundamental set? Yes, we will, but let's actually verify using the Wronskian that y1 and y2 are in fact linearly independent. So the Wronskian of these two functions, right? It's our determinant, and so we'll have the x to the 4th and the natural log of x times x to the 4th. And now we need to put the second derivatives the first derivatives in the second row. So this is 4x cubed, product rule again. So we got 1 over x times x to the 4th plus the natural log of x times 4x cubed, right? So this simplifies to x to the third power, right? So let's go ahead and compute the Wronskian. So we have to take x to the fourth and multiply the quantity x cubed plus the ln of x times 4x cubed minus the ln of x times x to the fourth times 4x cubed. So what do we have here? So if I distribute this, I'll have x to the seventh, and then I'll have plus, I'll write the polynomial first, so 4x to the seventh natural log of x, and then minus, look, we got the same thing here, 4x to the seventh times the natural log of x. So that the natural log of x, those terms go away, these, and we're left with x to the seventh. Well, again, this is where our existence, our interval of existence comes into play. Since x is greater than 0, x to the seventh is never equal to 0, right? So if x is a positive number, then x to the seventh is always going to be a positive number, right? So it's never going to be equal to 0. So y1 and y2 are linearly independent, and we got it. Where's the fireworks? Where's the confetti? So therefore, here's our, now we can claim that we have a fundamental set. So let me write it like this. Right, so this is a fundamental set of the DE, and by the superposition principle, why did I write by twice? So no, I'm not saying by, I'm not done just yet. We're getting there. So by the superposition principle, the general solution is y equals c1 times x to the fourth plus c2 times x to the fourth times the natural log of x, right? And there you go. So it turns out, and we'll state this as a theorem. So what happens is, in the repeated case, when you have a Cauchy Euler equation, instead of multiplying your first function that you can get by using algebra, instead of multiplying this by x, like what we did in the previous case, you multiply it by the natural log of x. And again, you can see having the natural log here, it forces this condition again. Notice how many times this condition that x is greater than 0 is helpful, or is kind of justified by the more we reveal in this process, the more we see how this simple condition that comes from our existence and uniqueness theorem, how useful it is. All right. So let's state the theorem now in general, and then we have case 2 covered, right? So if the auxiliary equation of, again, and let's write down the general Cauchy Euler, second order Cauchy Euler that we're working with. So if the auxiliary equation of that equation has real repeated roots, and let's say m1 equals m2, and let's just call it m, then the fundamental set, right? So the fundamental set is, here are the two functions. The first one is easy. It's the x to the m. The second one, I mean, you write it down, it's easy, but it's what we had to do to get this. That wasn't an easy process. And you're not going to replicate the reduction of order process. You get to use this theorem from now on. So that's our fundamental set. And the general solution, as we've gotten so accustomed to using that superposition principle. So our general solution is y equals c1 x to the m plus c2 x to the m times the natural log of x. All right. All right, let's do another example of this, kind of showing you, okay, now that we have this theorem, what exactly does a full problem look like? And we'll solve a general solution. I won't do an initial. Actually, yeah, let's do this. So let's do an example, and let's just say solve. And it is 4x squared. There's it times my second derivative. Plus 8x times my first derivative. And then plus y is equal to 0. All right. So there's our differential equation. And again, we'll just find the general solution. So our auxiliary equation, right, for the Cauchy Euler, remember it's slightly different in the first term here. When it switches over to that algebraic form, you have 4m times m minus 1, and then you'll have 8m and then plus 1, and then that's equal to 0, right? So again, let's write this quadratic in standard form. So we'll have 4m squared minus 4m plus 8m plus 1 is equal to 0. So again, we always have that pair of like terms in the middle. So we have 4m squared and then plus 4m plus 1, and then that's equal to 0. And again, if you look closely at this, you can see that this is our perfect square, 2m plus 1, that quantity squared, right? So therefore, our m1 and m2 are the same. It's negative 1/2, right? So here is the fundamental set, or I'll just say basis. And it's so the first is the power function x to the negative 1/2. And then again, because this is now the repeated case, the second function is the same power function times the natural log of x. And clearly, if you don't want to write this as a power function with a negative fractional exponent, you can write it as 1 over root x, comma, natural log of x over root x, right? And then let's write down our general solution. So our general solution is now all the possible linear combinations of these two functions. So y is equal to c1 times 1 over root x plus c2 times the natural log of x over root x. And again, another way you can write this, which might help, for instance, when you have, let's say we had conditions and we had to solve for c1 and c2, and if there were initial conditions, you'd have to do a derivative. Since you have the same power function here, you can actually factor it out. So another way that this can be written is 1 over root x, and then in parentheses we have the quantity c1 plus c2 times the natural log of x. Lots of different ways you can express it, but now that we've done the hard work of the reduction of order process, we know what the pattern is whenever we have our second case where the auxiliary equation has a real repeated root. All right. And up next, you know what's coming, complex conjugates. Can't wait for that. See you soon.